Let's do it. Welcome back, everybody. So we're going to basically just start doing examples before we get into something else. So I want to teach you how Bayesian kind of operates, teach you more about likelihood functions and whatnot. But what we learned last time is that a likelihood function is the same formula as the sampling distribution. You can exclude the normalizing constant, so things that don't depend on the parameter. And it's the same function, but it has a different argument. So it's a different function altogether. It looks like the same formula, but it's a function of a different argument. The data is plugged into your likelihood function, and you treat the parameters as the variable. Now that's a little bit different than a sampling distribution in that you let the data, it's a function of the data given fixed parameters, and we call the function of the data a random variable. So the data is a random variable, and that's a special property. That means that it adheres to rules of probabilities. What a Bayesian is trying to do is upgrade the likelihood function to a probability distribution or density, depending on if it's discrete or continuous. And sometimes I mess up and I use those terms interchangeably. And oftentimes I use the same f to define my function, but they're different functions. So let's just be nimble in all of that. But I think examples are where we're going to get the most insight right now. So I'm going to simulate this example. We'll play around with this example a little bit later. Now I want to point out the notation I used, f of x, is a little bit misleading. And this is the way you'll see it done in most probability classes. But I like to be a little bit more specific. I like to tell you where the conditioning is. And so this isn't just because I'm a Bayesian, it's because I like to describe everything the way that it is. I think it's important. So I like to write down f of x given p, so I know what is given. You won't see that in all of your classes. But I like to be really specific about it. So this one right here, I would say, this is f of x given mu and sigma. Sometimes I'll mince my notation again, so if I tell you that you know sigma and you can just not worry about sigma, sometimes I'll leave it out of the equation. Sometimes when I'm just trying to learn mu, I'll just put it over here, but this is the real description. So I can't talk about a normal distribution until I tell you its mean and its variance. Otherwise, I'm talking about a general class of distributions. And so this is a family of distributions if I don't tell you what mu and sigma are. So it's a family of normals, all of the normal distributions. When I tell you what mu and sigma are, you can sample from that distribution. It's a specific normal distribution. So I want to describe this point to you just a little bit. Let's think about the binomial case. So this is a coin flipping model. And a lot of times we like to think about a coin being flipped with a fixed probability p. Now, I'm not sure if that's actually realistic, but it's close enough that we can use it. So every time I flip a coin, maybe I change the parameter a little bit. Maybe it depends on who's flipping it, how high I flip it. But the idea is that it's random, it's the same process over and over and over again. So I want to exemplify this point a little bit. So let's just look at an example and simulate from a binomial. Now I think I can change the font here. I think you guys always want me to change the font. Does anybody know where the font is? Somebody probably knows. Yeah, where is it? Probably should have thought about that this morning, but I just thought about it right now.
You do like Control Plus, everything highlighted.
Yeah, but I want to do it throughout the whole editor.
You can go to Home Settings.
Home.
Preferences.
Preferences. To the right. Right.
Right.
Oh, cool. Right on.
Can I scroll more? One of the
Oh,
triangles.
boom. Nice. Is this it? Let's try 14. Let's try 2018 maybe. Desktop code font, monospace. Does this look right?
Yeah.
Oh, nice. Thanks, you guys. Sometimes I need help too. Okay, so I'm going to be specific about this binomial distribution that I'm sampling from. Now I'm just going to flip the coin once. And Bino-Ran does that with this argument with a 1 in there. Every time you invoke a function in MATLAB or R or whatever, I want you to go to the help file and look at how they parameterize that distribution. It will save you hours of debugging. Sometimes you think your code is wrong, but you've misinterpreted what you think the distribution is. So sometimes I write the distribution in a particular way on the chalkboard, and things like R might flip some stuff around. I'll try to be as specific about that when we get to those examples. In the Bino, in the normal, people haven't been too creative with this, and they stick to the same convention. But things like exponentials and gamma, there's some differences there. When we look at those examples, I'll try to remind you. You might remind yourself after spending 20 hours trying to debug something. I've seen this happen. I've certainly spent a few hours of my own life messing that sort of thing up. Now I don't. Okay, so this distribution right here has p is equal to 0.7. So the probability of getting a 1 is 0.7, meaning that if I flip the coin, a lot of times, about 70% of the observations will be 1 and about 30 will be 0. And so this is the coin I'm going to flip. And the question is it important that I tell you what P is? I'm going to try to make the point that it is. Now, I'm going to black out my projector just for a second. For totally arbitrary reasons. Black that out again. Says 0.7, it says n is equal to 20, so I'm going to flip this coin 20 times. So let's see how this does. I'm going to let you see all of these observations as they come through. So our first observation is a 0. I'm going to flip it 20 times. I see a 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0. Get rid of my pause statement. That's how I slow things down in class for you. Just watch this again. Let's do it like this. Count these things up for you as we do this. Let me just put a counter in here. And I'll tell you what the sum is after everything. The semicolon suppresses the print. Oops, got 0.7. Everything's good. Let's just do this again. Boom. Let me tell you what the sum is. Sum is equal to sum plus draw. Sum is equal to 0.
project limit?
Yes.
You never actually said P to 0.7, it's still 0.2.
I know. You haven't seen it on the right, can you? That's actually my point.
Oh.
So, that I'm going to try to make. And you've sniffed me out already. So let's just run this thing again and just see what happens. So you can see my workspace, and I should have blocked that out. What I wanted to tell you in all of this is I go through this summing that if I don't tell you P, these things aren't independent, and you would be able to figure it out, that it can't be 0.7. I keep seeing over and over again an overabundance of zeros. And so telling you what P is extraordinarily important. The data is informative about that P in the first place. So if I told you it was 0.7 and it was really 0.2, without looking over on the right-hand side, but good job, you'd be able to figure it out eventually and say that I actually lied to you. The number is actually 0.2, and the data is informative about that. So what that tells us is that the data is not actually independent. It's the data given all the information about the model. So if I tell you the model, then everything is independent to you. If I tell you what P is, you can't learn from the data. You already know everything there is to know. And so that's what this exercise was supposed to tell us, but I forgot it tells you everything right up here. So that's what I was doing is I blacked everything out because I was trying to trick you, but you guys are too good for that. So it's only when you know what the distribution is and you know all of its underlying parameters that the data you can't learn from. What we do in statistics is we learn from the data. What are we doing? We're learning the model. In a class like this, when I tell you what the model is, you're learning the parameters. That's what the data is teaching you. That's what we use to forecast. So if all data was independent, and we misinterpreted what that means, would tell us that we can't learn from data, and that we can just forecast out of what we already know. What we're actually doing when we predict is looking at the data, learning the model, and then forecasting out of that. I think that's an important concept. So it's not just notation that we write down, but rather it's notation and it means something to us. So it's not just that I'm Bayesian and I want to do the conditional flip and I'm setting you up for it, but it's a real description of what's going on. Hopefully I'll have better examples in the future. And hopefully you guys all understand that. Okay, so I want to just walk through this a little bit and show you what a Bayesian does. So let's start with a binomial example and just think about Bayes' theorem. So first question is for the binomial is what's the likelihood? And I'll just give it away. It's this thing. But it's a function of P. The first thing we notice is that P doesn't show up there. And all I'm interested in is the parts with P in there. And so I would say this is the kernel of my distribution. Okay, so that's what I'm usually thinking about. So this is the kernel. What that means is that it's everything you need to know about the model. It expresses the relationship between the data and the parameters. So relationship between data, in our case that's X, and the parameters. That's key. Okay. And this is it right here. This is the only part you need to know. So this part isn't relevant in describing the relationships between P and X. That's the part that I call the kernel. Just this part. I circled too much the first time, so I'm on a roll. But this is the kernel of the distribution. This is the normalizing constant. If I were talking about x and I wanted to understand x, I need that part of the equation. But if I'm trying to learn p, I don't need any of that. And so the likelihood is just proportional to the kernel of the distribution, but I'm changing my mindset and thinking about this as a function over the parameters. So our likelihood function, I like to write it down like this. LP given x. And often I write it like this. P to the x, 1 minus p to the n minus x. So this is the number of my successes right here. This is the number of my failures. It's multiplying the probability of getting a 0 or a failure, if you're familiar with that convention. So I'll use words like that kind of interchangeably: successes, failures, heads, tails, and hopefully you can insert what I actually mean. Oftentimes we use log likelihoods when we do computations, and it's kind of unfortunate that when I take a logarithm over this thing and don't have a good symbol to express that it's the same log likelihood up to summing any arbitrary constant. So unfortunately, we don't have any notation for that. I don't know why. Maybe we could create it. So, but I will use this notation all the time. Proportional to. And that means I can multiply by any constant, it's still the same likelihood function. So likelihoods are relative to themselves. We've said that before. So this is the first ingredient in being a Bayesian. There's only one other thing, and that's the prior. So I'll ask the question, which prior should we use? And don't feel uneasy if you don't feel good about coming up with an answer to this. This is the whole thing that made people uneasy about Bayes in the first place. Which prior do we pick? Does that mean that I know what P is already? I'm putting a probability distribution on P. I'll give that some notation. So pi P. But we might want to ask ourselves some questions about what would good properties be for a prior. So before we answer the question, which prior, let's just talk about properties. So what properties? So I don't think it's fair to say we're going to insert our information about P, because if you didn't know how I picked P in the first place, you wouldn't have good reason to invoke any properties. But we might have some mathematical properties, some properties that we usually invoke in statistics, and we think statistics with certain properties are better than other statistics. And so that's the real answer to which prior, depends on which properties you want. So what are good properties? Anybody want to be brave and kind of answer? What would you like?
You mean like a coin flip is probability of 50%?
Say it again.
The coin flip is assigned at 0.5.
So a coin flip might be assigned. So I might want to make, before I go into the analysis, say that I think the coin flip might be 50-50. So, okay, that's a pretty good property. I like that. So maybe before we see the data, we think P is 50-50. I'll give that some notation. So we think P is 0.5. So we think the coin is maybe has a 50-50 chance of being a 1 or 0. P is unbiased towards one or 0, i.e. it's 50-50. Why do you like that? What makes you like that? It feels pretty good, right? I think all of us might be inclined to say, maybe that's a good thing. It depends. So if I was walking around with loaded coins all the time, that wouldn't be a good choice. But I think the idea is not to bias one side or the other. I kind of like that. Is that all we want? So if I said P is absolutely 0.5, no data can steer me away from that. So I could say that just coming in. It's 50-50. That's all there is to it, and you'll never change my mind. And so we want the data to weigh in also. And so we need more properties. Anybody have any other properties? I kind of like your suggestion, and I use that all the time. But there's more to it. Yes, please.
I mean, in another direction, you can say it's equally likely, so P is a uniform distribution. Or
Maybe a uniform distribution. I kind of like that too. So maybe uniform. Now, I'm not saying that this has to be the case, but you kind of like the idea that maybe my prior should look like this. So as a function of P, this has to live between 0 and 1. So I would say this is probably the first thing I would invoke, is say P has to belong to be in the interval 0 and 1. If it's not, then I have a problem because that's not the state of my model. My model has P being between 0 and 1, so my prior better live there as well. And so you said, let it be uniform. So maybe that's a good choice right here. So this is going to be pi P is going to be equal to 1, where P lives between 0 and 1. Not a bad choice. Anybody else have any other recommendations? I think people like this. You know, most humans I know, they say, put uniform priors on stuff, because that's going to make sure that I'm not informative about everything. If I looked at the expected value from this distribution right here, it would live right here, 1/2. So instead of saying P is 50-50 and being absolutely certain about it, maybe we calibrate the expectation to be 0.5. And that's what you've done by doing this. So you've at least satisfied one of the things that we maybe want. Now again, if you knew a lot about how I selected coins, you might change your mind. Yes, please.
So one of the things I just heard is that in choosing your prior, if you are more certain about how your data looks, you choose a prior with smaller variance.
Yeah, so the variance has something to do with this. So the variability of everything has something to do with it. So Danielle says, maybe we want less variance than this. This has a lot of variability. And this is maximally variant. So, and you can convince yourself of that. You can come up with a proof of all of that. So, but maybe Danielle says, I want it to look like this. So Danielle wants to shrink the variability around 0.5. Now, if we were going to be absolutely certain about this, we might pick a prior. If I wanted to shrink the variability, then I might pick a point mass and say my distribution is just this sharp point. It would be infinitely high to come back that I have no width. That is a probability distribution. So they can't draw it on the board because it would go all the way past the sky. And so that would be the minimal variability thing that has expectation of 0.5. So it's really a question about variability. And statistics is all about variability, controlling variability, reducing variability in our estimates. Now, it would be really hard to answer which one we should pick if we don't think about the data. We don't think about this function as well, right here. So our answer probably has something to do with this function in itself. We'll talk about that later in class. Anybody else have any other suggestions? Pick a prior that's conjugate. I kind of like that. So, conjugate. Give myself some more room here. Maybe prior should be conjugate. Now Peter knows something. And he's given us a word. We need to learn this word. So these are very important types of priors. What are they?
They're priors that set up our posterior system.
Yeah, so it's be a little bit more specific. Conjugate priors have the property that our posterior distribution falls into the same family as the prior. There's only one of those that exists for any distribution. For some distributions, they don't exist at all. So it's kind of nice. So conjugate priors. Write this over here. If the prior I'm going to write this down as pi p is an element of some family of distributions Now, I don't mean something like the exponential family. That's a family of families. That's too big. So what I mean by family is something like binomial, normal. So distribution belongs in a family. So for instance, a normal distribution with unknown mean and variance is a whole family of normal distributions. So if my prior belongs to that family, then the posterior, I'll say pi p given x, is also an element of f. And these are the same. Then, pi p is conjugate. You'll see this word floating around mathematics in lots of different contexts, and it often means something entirely different in different branches. So in Bayesian statistics, you invoke this word, and it always means the same thing. But if you go to your linear algebra class, it means something totally different. Okay, there is a relationship, but don't overthink it. So for this right here, you can always figure out the conjugate prior just by staring at the likelihood function. So Bayes has these two parts, the prior and the likelihood, and they're going to multiply into each other. And so what Peter's suggesting is that I picked some multiplier so that when I multiply it into the likelihood, my posterior is of the same family as the prior. So what that means is that I'm not updating the family of models when I see data, but rather I'm just updating the parameters in that model. And so it's very useful for sequentially updating everything. It's also very useful if I just have a piece of chalk. So if I know all the properties of my prior, then I know all properties of my posterior. That's kind of nice. So for this likelihood function, what would be the conjugate prior? And I know a lot of you know the answer to this. So not all at once. Beta. So if you don't know that and you wonder how Peter knows this so easily, it's because he took a class in this week. Good taught it. So for the binomial, pi p is equal to a beta, and a beta has two parameters in it. I'll show you what it looks like in a second. So it has an alpha and a beta usually. So this is a little bit cumbersome to talk about because the distribution is called beta. It has a parameter in there called beta. So I'm using those words different. So beta looks like this. This right here is the inverse of what's called a beta function. So I've just used the word again in a different context. So this is a beta function. And it's actually the inverse of the beta function. So what is a beta function? It looks like this. Integral p to the alpha minus 1 minus p to the beta minus 1 dp. And I'm going to integrate this. And this is what my beta function is going to be. It's defined to be that. I integrate between 0 and 1. It turns out that in a lot of cases, this doesn't have a closed form solution. So it turns out that if alpha and beta are integers, you can write this down using factorials. It's going to have something to do with gamma functions, if you know what those are. And so if you don't know what they are, I'd say just go to Wikipedia and look it up. It's really just the normalizing constant for this model. So this is the thing that normalizes it. So if I integrate over that, I divide by its inverse, it means that when I integrate over this whole function between 0 and 1, it will sum up to 1. And that's all it's doing. It keeps all those numbers living in any interval, living between 0 and 1. So a beta distribution is this. It has an argument that we call beta, and it's normalized by a beta function. I apologize for that. I'm not going to change all those words for you because it's what everybody else uses. So this right here is a beta distribution or a beta density. So let's just see what Peter's talking about and do our Bayesian setup and multiply the likelihood function times the prior. So in our case, pi p given x. So this is our posterior distribution. What we think after we see the data. This is our posterior. This is going to be equal to our likelihood function given x times our prior. And we're going to divide it by the integral over this thing. This will make it so that it's bounded between 0 and 1. Now the important thing in our posterior distribution is just this. All of this is just normalizing constant. So a lot of times I just throw it away. I don't think about it. I certainly never compute it. Okay, maybe not never. I can think of some examples, but usually. This is just a normalizer. This is our likelihood. And this is our prior. So this is the important thing. So let's just write out what that looks like. Now, I've already told you I can throw away my normalizing constants. If I throw away this thing and I don't think about it, there's no reason to write down the normalizing constant from the sampling distribution in the first place. So I'm just going to write down our posterior is going to be proportional to, and you'll see me do this throughout this class. It's really just a shortcut, so I do less math, but I get the same answers. So this is going to be p to the x, 1 minus p, n minus x, x. Times p to the alpha minus 1, 1 minus p to the beta minus 1. This is my prior. And so, I got it.
What about the beta inverse curve?
Yeah, I threw it away, right? So I could have thrown this normalizing constant right here and choose x. And I could have thrown this thing down right here, the beta alpha beta inverse. And I've gotten rid of that. And I've gotten rid of that when I wrote this all down. And the reason why is because as soon as I write down proportional to something, all of those constants can be thrown away. So the normalizing constant to the prior can be tossed, the normalizing constant to the function can be tossed, because I've written down proportionality. Now, if you want to write it down and carry it through and work with it, you can do that. But just keep in mind, you would end up writing it down in the denominator and they'd cancel each other out. So there's a cancellation. So let's just see that. So I could write this down using all of the little bits and pieces. So, and choose x. This is going to be the only time I do this in this class. So x, 1 minus p to the n minus x, beta, alpha, beta, whatever this number is, inverse, p to the alpha minus 1, 1 minus p to the beta minus 1. And then I divide by this whole creature. Same thing, and choose x, p to the x, 1 minus p to the n minus x, beta function, inverse, p to the alpha minus 1, 1 minus p to the beta minus 1, dt. And I'm going to integrate that between 0 and 1. So again, this is all just a number downstairs. Look what happens. That cancels that because it can be factorized outside of the integrated, outside of the integral symbol altogether. And that cancels that just because they're numbers. And so it doesn't have any relevance on the shape of this function. It just raises it up and down, but the curvature remains exactly the same. So I always throw that away. I never even deal with it. So as soon as you throw away one normalizing constant, you can toss all of them, because everything's just up to proportionality anyway. So I could work with this whole thing. I could try to figure out what this integral is, but this integral right here is going to be some other beta function. The key point is that everything is proportional to this thing. So So let's just see what we get at the end of the day. Ignoring the height of this distribution, this whole thing is proportional to p to the x plus alpha minus 1 minus p to the n minus x plus beta minus 1. And so my posterior distribution is proportional to that. What distribution or family is this? Beta. So not binomial. If we were to think about it in a function of x, it would be binomial, but this is a function of p. That's why it's on the left-hand side. So this is a beta. Which beta is it? This is really a beta density. And it has two arguments. Those arguments are right here. So remember our arguments of our prior for alpha and beta. They sit in front of that leading minus, they sit in front of the minus 1. So I never absorb my minus 1 into the n or anything like that. I always leave it dangling so that I can recognize the parameterization of this distribution. So this is a beta density with parameters x plus alpha and n minus x plus beta. Now I'm going to give these an 8. These are the parameters underlying our prior distribution. These are the prior parameters. Now there must have been a computer scientist hanging out next to a statistician, because computer scientists usually come up with cooler names for things than statisticians do. It'd be awesome if these were just called prior parameters, because they would like to know what it is. But people didn't want to be too obvious about this, so they call these hyperparameters. So the parameters that underlie your prior are called the hyperparameters. So if you hear somebody say, what are your hyperparameters? How did you pick them? They want to know how you biased or controlled variability in your posterior or your prior. So they're asking you about those settings. And this is a very important question. So how did you pick them? So hyperparameters right here. But the key point is that this is a beta density because we use the conjugate prior. So the prior is a beta. If it's conjugate, the posterior will be a beta. And the only way you can figure out what the conjugate priors are is to know what those distributions are to begin with. So you have to just learn all these distributions and kind of mentally multiply that prior through and think about what form would give me the same form in the posterior. So you have to use a little bit of imagination when you do this. I don't know any other way. And after a while, you get good at it. You're like, oh, I know this because I know what that distribution is. And so there are books that will have everything tabulated if you're ever confused. There will be distributions you're unfamiliar with. And so you might look these up periodically, or else you use your imagination. But sometimes your imagination might give you the form and you don't know what it's called. If you know what it's called, then you can invoke it on your computer. If it's not been named yet, you came up with something new and you can write a paper. So the question is how do we pick alpha and beta? Yes, please.
Do we typically assume conjugate priors?
I would say most people typically default on them. But I use other things as well. And so conjugate priors make our lives easy. But that's not a good reason to do an analysis using a conjugate prior. So there have to be other reasons. So it turns out there's a lot of properties that we do like, and the prior that it will induce will be a member of some conjugate family. We'll be studying that throughout this class. So quite often, I use them regularly, but not always. Okay, so I'm going to have to teach you about other types of priors. But we're going to start with conjugate priors. Yes, please. Jenny.
Professor, I'm curious. So these assumptions that we are making, right, do they necessarily tell us the truth about the data?
That's a good question. The assumptions we make, do they tell us the truth? Nothing tells you the truth. You will never know the truth in your whole entire life. That's the only true thing you'll ever know, is that you will never know the truth. But they bring you in the direction of the truth. So as I see more and more data, if my prior isn't too informative, then I'll start getting to the truth. But I don't think you ever actually know it. But you want to be close. So we want to be able to do something that's useful. So we want our priors not to be too informative. Now, here's a question for you. Somebody said we want maybe a uniform prior because that feels good to us. I'll try to convince you that you shouldn't feel too good about that. But somebody said we wanted expectation to be maybe 0.5. And then somebody said maybe we want a conjugate prior. We'll have to start honing in on the reasons why we might want this. But can I have all of those things simultaneously? Is a uniform distribution a member of this prior? The answer is yes. So a beta 1,1 is a uniform. So beta 1,1 is going to be a p to the 1 minus 1, 1 minus p to the 1 minus 1 is equal to 1. And it lives between 0 and 1. So what's the beta function for this? It turns out it's 1 as well. And the inverse of 1 is 1. So this is a uniform. Now, I want to just point out, most people do not use uniform in this example, but we can see how it works. And I think I'll leave you with that, and we'll pick up next time with this piece of code. But I wrote a piece of code, and some of you have played around with this before. But I want to show you what this looks like. I'm not going to walk you through this whole code. Eventually, I'll post this for you. But I have a piece of code that takes in some arguments. It takes in true p, and the only place that I use true p is plotting where the truth is. So we can answer Jenny's question, do we arrive, are we at least arriving at the truth? It takes in my hyperparameters, alpha and beta, and then I tell it how many iterations we're going to play with. So if I were to do this right here, grab this right here. I'm going to sequentially look at what this posterior does. We'll come back next time because this will just be too fast. So let's imagine true p was 0.2, and I was trying to learn that. Maybe we like a uniform distribution as our prior. So that's beta 1,1. And let's flip this coin 10 times. See what happens. So here's my truth. That's the only place I use this. I also use it in simulating the coin flips. That's it. I don't use it in my inference. Here's my prior distribution. It's uniform. It's flat. I'm going to flip the coin. I saw a 0. And here's my likelihood function. My likelihood function multiplied by my uniform prior is exactly the same thing because I multiplied by 1. So my posterior and my likelihood are the same. So what is that function right there? I saw a 0. It's 1 minus p is that function. So it's a straight line. So 1 minus p is my likelihood. And when I normalize it, that's my posterior. I do it again. Here's my likelihood function. I'm multiplying by 1, so my likelihood and my posterior are exactly the same. I update it, and that's my posterior inference. So what that's telling me, this is a 0 right here. I've seen a 0 and a 1, and it says p cannot be 0, and it cannot be 1. That's why it comes down to 0, because I've seen both of those. I've seen a 0 and a 1. but I'm pretty uncertain. There's a lot of uncertainty about what I think P actually is. I flip the coin again, and that's what that function updates to. So this function right here is I'm just inserting in these different arguments, and it's incremented now to 3. I know what alpha and beta are, and I know how many successes I've seen. I flip it again, I flip it again, I flip it again, and this posterior is getting tighter and tighter and tighter. It doesn't tell us what the truth is, but the truth certainly is inside of the massy part of this distribution. And as I flip that coin more and more, this curve, this density function will start to hone in on what the truth is. Let's come back next time, play around with this a little bit, and then we'll switch gears and we'll go to the formalization. Thanks, you guys.